Hello everyone, welcome to this video. Today I'm going to give a tutorial on how to perform automated multi-tile imaging on the TESSCAN Mirror 3 scanning electron microscope with an external scan controller using Python and C++ scripts. This video will be complementary to the documents that you will find online for this project, and I hope it can provide a nice step-by-step visualization of how to use this code. So, first, a little bit background information. This project was developed to perform multi-tile imaging during in-situ mechanical testing, where the sample was screened by a miniature loading stage inside a scanning electron microscope, and at different stages during the loading process, we paused the experiment to capture SEM images of the sample. This is often combined with digital image correlation, where the image of the deformed sample was compared with the reference or undeformed sample to perform full field deformation measurement. Such type of experiment can benefit from developments in two aspects. One is the ability to image a large sample area of interest, and the other is the ability to capture images with high resolution and low distortion. And the code of this project has the benefit in both of these two aspects. The first benefit of using these scripts is that we can perform automated and customized multi-tile imaging to cover a large sample area of interest with many individual images that have a manageable image size and resolution. In fact, many of the SEM systems may already have a built-in function for this purpose, and sometimes they might even be a better solution. But having a customized script means that you might get some additional flexibility for this process. For example, in our in-situ experiment, we capture the reference image tiles at a regular grid of positions. When the sample was deformed, the area of interest may have been deformed, may have been slightly rotated or stretched irregularly. So it's better not to have the image tiles aligned perfectly horizontally or vertically. And our solution is to control the position of these four corner image tiles. And the rest of the image tiles position are then determined by a bilinear interpolation. Another benefit is that optionally, you may choose to use an external scan controller, which might result in reduced image distortion, depending on your SEM system. I have worked on different microscopes and observed different types of image distortion, as illustrated here. So, for example, if you perform DIC on a pair of images with a rigid body translation of your sample between them, you should expect no strain fields to be measured. However, for images taken on an FEI Tenniel microscope, we observe these vertical lines of artificial strain fields. And for images taken on a TESSCAN Mirror 3 SEM, we can observe these cross-hatch-shaped artificial strain field. And with the application of an external scan controller, such type of image distortion can be significantly reduced. Another example is when you want to stitch two adjacent images with an overlap area between them. You may find that the relative positions of different features, for example, these four windows, may appear differently on different images. For example, when features on windows 2 and 4 are overlapped well, then you may find a relative shift of these feature positions on windows 1 and 3. And with the external scan controller, such type of distortion may also be significantly reduced. Now let's look at how to get these codes running on your computer. First, we can go and download these Python scripts from GitHub, which also includes the Shark SEM API library that comes from Tescan. We can simply follow this link and download this zip file and copy it to a folder that we want to put our codes in. For example, here, and extract it here. The scripts for the automated multi-tile imaging on the Tescan Mirror 3 SEM is written in Python. And to get Python running on your computer, you need a Python interpreter and an environment management tool, such as a Miniconda or Anaconda. And my suggestion is that we can simply install the Miniconda distribution of Python. And to do that, we can simply Google search for Miniconda, go to their website, download this installer, and then we can just follow these default settings to install Miniconda on your computer. A virtual environment is something unique of Python, which is different from some other languages such as MATLAB. For example, if you have a Python project that requires certain version of the interpreter or certain packages, you can create a virtual environment and install everything inside this environment, so it does not conflict with some other projects which may require other versions of interpreter or other packages. And since now we have downloaded the codes on our computer, we can try to run it. We can open this Anaconda prompt and cd to the directory that we put our code in. We can see that these are the codes we have downloaded. The sem.py and semcon.py are the API that comes from Tescan. This semcontrol.py is the scripts that I wrote for the automated imaging. If we try to run this code, Python semcontrol.py, we can see that we don't have these packages installed yet. So we can create a virtual environment by following these instructions. To create environment, we type conda create -name, we call it Tescan, and proceed. Now we can check the environments that we have. Conda in list, we can see that we have the base environment and the environment we just created. But we're now in the base environment indicated by this marker. We can activate the Tescan environment we just created, and then install all these packages that are required. Now the second package, we install it from CondaForge channel. And then the third one, now we're done. And this command, conda list, we can see that it lists all the packages we have now in our environment. To get the scripts running, you also need to have the TestScan user interface open, so the microscope and your Python program can communicate with each other. And for the purpose of debugging, it's also nice to have this demo mirror TC installed, which is a software that comes with TestScan installation. And it is like you are having a user face that is communicating with a virtual microscope, and you can operate that microscope using the interface or control it with your Python program. And you can see now I'm having this virtual microscope running. Now we can type in Python semcontrol.py to run the script, and we can see the user interface. Here, for the meaning of these parameters, nr and nc means the total number of rows and number of columns of images you want to have to cover your whole area of interest. Field of view means this field of view size for each image, and the dwell time means how much time you want to spend on each pixel position. And here is the total of number of pixels on each image, and we are taking square images. For example, here a 4K by 4K image. IR and IC means your current position, which means you don't have to start at the upper left corner every time. You can even start in the middle, but the stage translation will always follow this snake pattern automatically. And on the right side, we have some read-only parameters. Here, it means like for the scan speed, beam intensity, and voltage, you always want to have them directly set up in your user interface. For the other imaging positions, how do we want to adjust the brightness, contrast, stigmation, focus? Here we have three options. Auto means use a built-in Python function for automatic focus, basically. But it seems that the Python function has some limitation. So another option is to use this interp. Basically means you set up the focus very well for these four corner positions. And then for the rest of the image positions, the focus position is bilinearly interpolated. And manual basically means you directly go to your this user interface, adjust the focus, brightness, contrast as usual, and hit continue in a pop-up window. For image capture function, auto means use a built-in Python script to capture image without popping up window for confirmation. Built-in means basically we are simulating keyboard input to use this acquire image option. So you have to set up your imaging parameters and your automatic save locations directly in this user interface. The menu means you just do whatever as usual in your user interface to save images. And external means we capture image and take the image using a external scan control. The executable for external scan control is compiled by C++. And for the usage of that script, I will talk about it separately later. We have other parameters that controls your image name, where you want to save your image, and where is the external scan control executable is located. And the remaining two rows corresponds to the position of these four corner image tiles. So if we hit set as current, so it reads your current position. That is your stages on your microscope. You can also directly input your position and hit go to and go to your desired position and hit set as current to record that position in the memory for this image tile. And for example, here we can go directly to some positions, record it, and we can switch between these each positions to double check the image quality. And after all this is set up, we can proceed to do the automatic imaging process. Right now, I am recording the desktop of our lab PC, and let's look at how the code works on a real microscope. I already have this Python script running and have some parameters set up. And first, we can try to use this built-in image capture function. And to use that, the dwell time and the image resolution here doesn't matter. And we're actually using our settings on our microscope. So the scan speed is taken from this SEM image parameter setting. So this setting, and we are using scan speed 3. That means it's only 1 second to take an image. We're going to just take it very quickly. And we also have this auto save function enabled, so it will automatically number my image and put it in this folder. Okay, now let's try to take images. The first image is taken, and the stage is moving to the second position. Now the second image is taken. And you can notice the translation of the SEM image in this live view. Now all the 4 images are taken and the stage is translated back to the original position. And next, I already have the external scanner hooked up to our computer, so we can try to use this external scan function. And this setting, we are using a dwell time of 8 microseconds at each pixel position, and the image resolution, we are using the input here. So 1000 pixels by 1000 pixels for each image. At each image position, the Python program is calling our external scan control function compiled by C++ programming. And it's indicating the process here, and this is the image taken by the external scan control. Okay, we can see that we have these 4 images taken by the built-in function, and for images by the external scan function. And we also have this time log created by external scan. Okay, now let's talk about the external scan control for SEM imaging. The external scan control program can be used either individually from the command line, or it can be used by the Python function. The principle and the setup of the external scan control is illustrated in this slide. So typically, during the SEM imaging process, you have a built-in scanner that controls the electron beam rastering process. For external scan control, in our case, we have this device, a National Instrument Data Acquisition device with model number USB6251 with BNC connector. And we use this device to generate signals that controls the electron beam rastering process. Also, the detector signal is also collected by this device, and we use the signals to form SEM images. The physical connection is like this. So behind our microscope, we have this electronics cabinet, and we can open these two panels on the left and right side of the electronics cabinet to reach for the terminals that we want to use. We connect these two analog output terminals of the external scan controller to these XEXT and YEXT terminal on this A30 module on the right side of this electronics cabinet. Usually, these two terminals are used by EDAX for the EBSD scan process, and we simply unplug their cables and we plug in our cables. We also connect one of these analog input terminal to this signal A terminal on the A05 module on the left side of this electronics cabinet. And during imaging process, the detector signal will come out of this terminal, and we collect those signals for SEM imaging. The connection between the external scan controller and your lab PC is simply made using this USB cable. To use the National Instrument device, we have to install the driver support from National Instrument. Here we can simply follow this link to the download website and select an appropriate version of the driver. In our system, we were using a relatively old version of the driver, but it is still quite a large file. So I have already have the file downloaded, unzipped, and installed in our system. But it is a quite straightforward process. You can simply follow the default settings and have the driver installed in your system. After installing the driver, when you plug in your device to your PC, the device should be recognized, and then you should be able to use the device. Optionally, you can create a virtual device in NIMax, which is the software installed with the driver for the purpose of debugging, so that you don't have to physically connect to the device for programming. And to do that, here we go to Device and Interfaces and hit Create New and select this simulated NI DAC MX device. And we can search for the model number, which is a USB 6251 with BNC connector, and hit OK. Now the device is created. We can also change the device name to, for example, device 2 and save it so that we can leave the device number 1, the name for the physical device. The external scan control scripts is written in C++, and to use that, you have to install a C++ code editor and compiler. You can use your favorite code editor, and in this example, we are installing Visual Studio Code for that purpose. So we can simply Google search for VS Code, go to their website, and download this installer. And then we can follow these default settings to install VS Code on your computer. To use C++ in VS Code, we also need to install the C++ extension. To do that, we can go to this extension manager and search for C++. It's already a popular extension, so it's already here. We can just install it here. What we also need is a C++ compiler. And the two common choices are either a GCC compiler or a MSVC compiler. And in this example, we are installing a compiler from Microsoft. So to do that, we can Google search for build tools for Visual Studio, go to their website, click this downloads, and search for these tools for Visual Studio, and download build tools for Visual Studio. You see the installer is downloaded. We will just run this installer, and we will select this desktop development with C++. And depending on your system, you might have to come back and select this older version of tools. And here we are just installing this version. After installing the build tools, the computer will restart. And now we just need a further extension, which is the CMake tools. So we can search for these CMake tools and install this extension. Now we can download the C++ source codes from GitHub following this link. And in this example, I'm downloading using the git bash command prompt. So pwd, this is the directory we are currently in, and I cd to the directory that I want to put my code in, and type in git clone followed by this link. Now it's downloaded, and I cd to this directory. Note that there are several branches, and if I type in git branch dash dash list dash dash or, we can see that there are 3 branches, and the updated code is in this develop branch. So we want to check out this branch. We type in git checkout develop. Now we have switched to this branch, and we can open the codes in this folder by typing in code dot. That opens all the codes in this folder by VS Code. Now let's look at how to compile the C++ code in Visual Studio Code. In Visual Studio Code, here we can click and select whether we want to compile a debug version or a release version of the code. Here we select release. And then we open the command palette by typing Ctrl-Shift-P and type CMake select a kit. So we can select this Visual Studio Build Tools 2019 release AMD 64, this compiler. And then we bring out the command palette again and type CMake configure. Then again, CMake build. This will generate a executable in this build release folder. So we can see this executable here. If we double click it, we can see that we are still missing some libraries, and the solution is simple. So we can go out to this FFTW folder and select these 3 DLLs and copy it to this release folder. And now, if we double click, we can see that this code is runnable. So this executable can be run from the command prompt. If I open a Windows command prompt and change directory to this folder, I can call this executable and add arguments. For example, -x means the terminal that controls the e-beam scan in the x direction. So it's device 2, which is the virtual device we just created. Analog output terminal 0 -y is the terminal controls the e-beam in the y direction. -e is the detector signal input that we use to generate SEM images. So it's analog input terminal 2. So this is the -h is the height of the image. So 2000 pixels in height and 2000 pixels in width. This is the dwell time that we spend at each pixel position. So 4 microseconds. -r true means we are using the raster scan. -o this is the output image name that we want to use, and -t is where we want to save the time log. So if we hit enter, we can see that this script is running, and we are taking an image using the virtual device, and soon we will see that the image is captured and it is saved here. Because it is just a virtual device, so there's no feature to capture. It is just a blank image. But here is basically how the code runs on the command line. And for the detailed usage of all the arguments, you can check the source code. And also, if you type something wrong, for example, -a0, you can also get a explanation of these arguments. So these are how to use the external scan control for multi-tile SEM imaging. I hope this video provided a useful explanation, and thanks a lot for watching.